Thanks, Matt. Thanks for coming. I really appreciate the opportunity to come and talk to you. I was originally scheduled to come here, I guess, in April of 2020, and it's a little foggy to me now, but something came up. So I'm glad I made it here today. The apocalypse took a little break. I'm going to talk again, as Matt said, about looking for dark matter at accelerators, and in particular, not colliders, but really lower energy accelerators, small experiments. And I'm going to start at the beginning. I'm sure this story is familiar to many of you. Maybe some of you know it better than I do. But dark matter, astronomical dark matter, is nearly a century old now. Actually, before it was discovered, people had actually been thinking about, well, maybe there's matter that we can't see in the universe. We should be looking for it. And they were looking for it. But there wasn't much definitive until, I think, the first that I'm aware of was Jan Oort in 1932, who was studying the motions of stars in the Milky Way, and was able to infer from that there was some large amount of mass in the galaxy that wasn't accounted for by the visible matter. And he even called it dark matter, although that was not a new term. That was the term given to this concept before that. And pretty soon Zwicky got involved in doing very similar work, rotations of galaxies. That work evolved until a very beautiful an encyclopedic work of Vera Rubin in the 70s, studying galactic rotation curves, using the delicate balance between inertia and gravity to infer that there were these large dark matter halos around all the galaxies that were being studied. Didn't take long before people started to think about, well, what is this dark matter? And I mean, when I was a kid and heard about this idea, I thought, well, it's probably just some matter that's dark. Can't see it for some reason. Maybe it's gas. Well, so, there were searches in the 60s and 70s, a number of them, that, looked for interstellar gas in various ways. Not much in the way in that era of great pictures that you can take and put in your talk, but there were some pretty colorful searches, actually. You can ask me afterwards, for this type of dark matter, and they really didn't find anything. Maybe there are dark stars, brown dwarfs, and they did microlensing searches looking for transits of brown dwarfs in front of background stars in the 90s and beyond, and they found some, but not enough to really account for the dark matter that we see. Then there's the possibility that maybe we just don't understand how gravity works at large distance scales, so-called MOND, or modified gravity. The problem is that we started to see these examples of astronomical structures like mergers of galactic clusters, where the distribution of visible matter and the distribution of mass in these objects are just qualitatively different. And that's pretty hard to explain by just modifying gravity. So there's this final possibility, maybe dark matter consists of some particles that just have weak coupling to ordinary matter. Now, that idea got a really big boost from studying the cosmic microwave background, which really is an astonishing thing, that these small density fluctuations in the early universe that have encoded in them the interplay between mass, gravity, inertia, and pressure in the early universe, left frozen in time and sort of cast through the lens of time across the sky as these small temperature fluctuations in the cosmic microwave background. And one can study the scale of those temperature fluctuations basically as the amplitude of those fluctuations as a function of their angular scale, and learn a lot of things about what was going on in the universe at the time that this light became free streaming. And what you learn is that there was dark matter of some kind. Okay, there was something with mass, couldn't have been stars, that otherwise had only weak interactions and that were present at that time, and that the abundance of these particles or this mass was strikingly similar to our astronomical dark matter. So that's pretty suggestive that our dark matter is some kind of particle. And then things went a little bit further, because one can study how this structure in the CMB, these density fluctuations, became the large-scale structures that we see in the universe. And what one finds is that these structures had to form, so to say, from the bottom up, smaller structures forming first and then joining to make larger structures. And that's in conflict with the idea that dark matter is relativistic. So dark matter has to be cold. And that rules out our single known candidate for some known, weakly interacting particle, neutrinos. So what kind of particles are these then? And now we confront the fact that although we know all this amazing stuff about dark matter from the things that we've studied, we actually really don't know very much about what it is. And basically all we know is that it's somewhere in this 80 orders of magnitude of mass range, where down at this end it's too diffuse. The de Broglie wavelength becomes longer than the scale of some dark matter structures that we see. And at this end it's too lumpy. We would see that in astronomical searches. Now across this mass range, there are some sort of favorite candidates. But in this mass range where it's useful to think of these things as particles, okay, there's one thing that all of these dark matter candidates have in common. And that's the idea of thermal contact. And I'll explain what I mean by that. So discoverable particle dark matter has to have some significant non-gravitational interactions with visible matter. So most discoverable candidates for particle dark matter had some kind of thermal contact with visible matter in the hot early universe. And that thermal contact often plays a role in generating the observed abundance. And that often leads to testable predictions, where a particularly simple and predictive mechanism for generating the dark matter abundance is so-called thermal freeze-out, or freeze-out of thermal relics. So basically, if in the early universe I have dark matter and standard model fermions, and there's some sort of interaction between them at temperatures that are higher enough so that the energy of these things is larger than their mass, I just have this reaction going both directions. And then as the universe cools, I start to have the dark matter annihilating away. I get less and less of it until the universe expands enough that the dark matter particles just don't find other dark matter particles to annihilate with. And at that point, I freeze out some density which is cosmologically stable, that relic density, which is stable until today. And one realizes that the point at which this freeze out occurs depends on the cross-section here for this interaction. So if the cross-section is larger, the annihilation continues for longer and I end up with less dark matter. And if it's smaller, I end up with more dark matter. So there's this inverse relationship between the relic density and the cross-section. So it turns out, we know what the relic density is, of course, and if I write that, so I know what the cross-section has to be approximately. And if I write down something like this, where I have dark matter and fermions connected by a weak mediator, and I write down the annihilation cross-section formula, it's proportional to dark matter mass squared over the mediator mass of the fourth. And I get a dark matter mass of something like 100 GeV. And that's kind of exciting. It's called the WIMP miracle, because we have other reasons to think that there might be new physics at the electroweak scale. So, so that, of course, launches the idea of, okay, so let's look for WIMPs. And that's, of course, something that you can do, and we have been doing, because they're all around us all the time, and we're traveling through a field of dark matter particles, and every once in a while, one of them will hit us and interact. So if I take a detector and put it deep underground where it's nice and quiet and there are no cosmic rays, it's basically a big bag of nucleons. These dark matter particles will sometimes hit it and leave a signal. Now it's a small signal because they're not relativistic. They don't have a whole lot of energy to give. But basically with a large enough detector and with small enough thresholds, you can do this. And of course, that's exactly what we've been doing. And so there's been this incredible, again, achievement. Basically a multi-decade program of improving our sensitivity and increasing the size of these detectors to dig deeper and deeper into the parameter space for where we might find interactions with these WIMPs. Now, searches for where we would most have expected to find something just haven't found anything yet. And I think within the next few years, we're either going to find WIMPs or we're going to rule out most of the easily accessible parameter space, because at some point you start to have backgrounds from neutrinos that we know are there, and that will make it much harder to make bigger detectors that can find these things. Okay, sorry, I need a sip of water. So in the presence of that, what should we do? Well, maybe we should start thinking about broadening what we're looking for dark matter. And one way that we can broaden the search for dark matter is to broaden the search for these thermal relics, because this freeze-out mechanism that I described to you actually works, over a broader mass range than just for WIMPs. It works in particular at lower masses, so between, say, an MeV and a GeV. And that's kind of intriguing because that would give us dark matter that's, at the same kind of mass scales as the stable particles of Standard Model. And one of the problems is that, the energy depositions in direct detection are going to be a lot smaller. So you have to develop new technologies. It's very hard to do those searches. And of course, people are doing that. Meanwhile, production rates are really large in this mass range in small accelerator-based experiments. We produce things in this mass range copiously in all kinds of accelerated experiments. Now, you notice I'm not calling these WIMPs, and they aren't really WIMPs. And that's because MeV to GeV thermal relic dark matter requires some new comparably light mediator to get the right annihilation cross-section for freeze-out. So again, if I write down this annihilation cross-section and I put in a mass lower than about 2 GeV, I get an annihilation cross-section that's too low in the sense that I will freeze out early and have more dark matter than we observe today. So that just doesn't work. You can't have that. You could have less. It could be a subcomponent, and you could have axions and other things too, but you can't have more. All right, so, to a lot of people, this is immediately a vexing thing. Wait, I was looking for dark matter. Now you tell me I need some new mediator as well. But, ordinary matter is only 5% of the universe. And we have all these particles and forces. Why should the 27% that's dark matter be any simpler? Why shouldn't there be an entire dark sector of particles and forces that complete this picture? So we know kind of what we're thinking about when we think about what dark matter could be, but what would a dark force look like? Okay, so there are a few possibilities for a new force carrier that obey gauge and Lorentz invariance. But a benchmark example here, both theoretically and experimentally, that I'll focus on quite a bit is the possibility of a dark photon movement. So if I have another photon, a dark photon, often called an A prime, in principle, it can mix with the Standard Model photon through loops of heavy particles, and that generates a small coupling between the Standard Model fermions and this dark photon that's proportional to some parameter that we usually call epsilon, where epsilon is in a fairly restricted range even for relatively large masses for these particles. So sort of 10 to the minus 4, 10 to the minus 2, or in some theories where this first loop is disallowed, maybe 10 to the minus 7. And so that gives us the interaction that we need to mediate this direct annihilation to give us our freeze out with alpha dark on the left with dark matter, alpha on the right with the Standard Model matter, and this epsilon mixing parameter in the middle. Now, if you look at this, it doesn't just give us something here for our freeze out. It means that we have this interaction between Standard Model particles and these dark mediators, and that gives us a way to produce them in experiments. Because where there are photons, any experiment where I produce energetic photons, at some rate I can also produce these dark photons, and it's at a rate that's typically reduced by epsilon squared. So there are a number of processes here that we can use. The one that I'm going to focus on the most is this dark Bremsstrahlung process. So in an analog to regular Bremsstrahlung, where instead of radiating off a photon, I'm radiating off a dark photon. Now that process is a little different than regular photon Bremsstrahlung, if you're familiar with it. And the reason is that the heavier product in this interaction is what takes away all of the energy of the incoming particle. So in regular Bremsstrahlung, the photon's usually very low energy, but here, this dark photon carries away nearly all of the beam energy. So it's highly boosted and emitted along the beam direction, the direction of the incoming electron. And when it decays, its decay products are also highly boosted and along the direction of the incoming electron, whereas this poor recoiling electron is left with very little energy and comes out at a large angle. So this is an important picture to keep in mind, and we'll come back to it a few times because it really shapes the design of the experiments that we use to look for these things, and where there's a really similar picture for other mediators. Okay, so this is a bit of an eye chart, but I promise I'm going to try to make it worth it for you. So it's about what happens to a dark photon once I produced it. Okay? And what happens to it once I produced it determines how I'm going to look for it. So if it's lighter than twice the dark matter mass, then if I produce an on-shell dark photon, it has no choice but to decay back to standard model particles. It doesn't have enough mass to decay to dark matter. Okay, so it has to decay back through this weak kinetic mixing to standard model fermions, and I have a set of experiments that look for that, where I say I'm looking for mediator decays to standard model or visible signatures. Where these searches are often going to be specific to the mediator because the final state here, the allowed final states depend on the quantum numbers. Okay. Now, if the dark photon is more than twice the dark matter mass, then presumably its coupling to dark matter is going to be larger than this weak epsilon. And in that case, it's going to decay preferably to dark matter. But in fact, we don't really need a real mediator here at all. It can be an off-shell mediator, okay? And we can produce the dark matter off-shell and really through any mediator. So here we have searches that we say we're searching for production of dark matter, sometimes called invisible searches as well in the literature, where these searches are largely agnostic to the type of mediator. I don't really care what's here. It could be a contact interaction for all I care. Okay, and the experiments in both cases, what they do is they measure or constrain epsilon squared, so the interaction strength, the coupling, as a function of the mass of this mediator. So that's my parameter space. Now, how I'm going to interpret these experiments also depends on this mass hierarchy, but in a different way. Okay, if the dark photon is heavier than the dark matter, then the only annihilation that can happen is this direct annihilation that I've already showed you, and that's proportional to epsilon squared alpha dark. And in that case, because alpha dark can only be so large and have a perturbative theory, there's a lower limit on what epsilon squared can be, because if I make it too small, again, I'm going to annihilate out too early and end up with too much dark matter. So I only really need to search down to a certain interaction strength, okay, to rule out this possibility of freeze-up thermal relics. Now, if the dark photon is lighter than the dark matter, then I can have so-called secluded annihilation. It's not proportional to epsilon at all. 2 dark matter particles gives me 2 dark mediators. They decay downstream. I don't know how. I don't know what sets the relic abundance. There are a lot of theories of secluded dark matter that explain this, but there's no really clear target, okay, for what epsilon should be or can be. So it's kind of a wide open search in this parameter space, okay, based on these sort of theoretical motivations for what natural values of epsilon might be. All right, so I'm going to talk about both kinds of experiments, but start with these visible searches where I have both a motivated thermal target and just sort of a wide open parameter space. So that parameter space is here. So epsilon squared, A prime mass. This is where those thermal targets are in that intermediate mass range, okay? And there are a number of experiments that have constrained this. Some of them were designed to look for this physics. Some of them just had data that could be reinterpreted or recast to look for it. Across the top are mostly searches for just simple E plus E minus or mu plus mu minus resonances. It's the most familiar thing in particle physics. So measure the 4 momenta of the E plus E minus. I can reconstruct this mass of the mediator. I can look for a peak in a invariant mass distribution where you have to realize that together with my signal, I'm always going to have this irreducible background of so-called normal tridents, okay? Because I can have a virtual photon give me E plus E minus pair of any mass. So I have this enormous smooth background always that's many orders of magnitude larger that I'm looking for a tiny bump on. So you have to collect huge amounts of data, all right? And so an example of this was an early search that we did at JLab to use an existing apparatus, these high resolution spectrometers, with an electron beam on a target. Magnet separates the plus E minus pair. You measure their forward momenta in these spectrometers. And you can do this search in the mass distribution where you're looking for a little tiny bump, where there was a test run in 2011 that at that time excluded some new parameter space, and some new data was taken in 2019 where we're still waiting for results. These kinds of searches are ultimately limited by the beam currents and acceptable detector occupancies. So if I want to dig down an order of magnitude here, I need 2 orders of magnitude more charge on target, 2 more orders of magnitude more beam current, and I need a detector that can keep up with that. And so there's a limit to how far you can push down. This is sort of, aggressive, the state of the art, what you're looking at. All right, so there's another possibility, and that's what's happening down here, which is as you dial down this coupling, you're suppressing that A prime decay, and it becomes long-lived. And at high boosts, it travels long distances before it decays. And that leads to sensitivity with so-called beam dump experiments, some of which were designed to look for just this kind of thing, okay, where I take a very energetic and powerful beam, put it into a beam dump, and then I have some thick shield of Earth and a decay region downstream where I put a detector. And if I produce something that's long-lived enough that it passes through here, where all the standard model stuff is completely shielded out and decays on the downstream side, I see a signal in my detector in time with the incoming beam, and I shouldn't see anything here at all. An example of this is this E137 experiment. It's LAC. It's a 40-year-old experiment. Very simple experiment. Still has some of the best limits in parameter spaces for a number of models. Unbelievably. The key background here is just cosmic rays that can hit this thing, or accidentals. They were worried about other experiments that were going on in the research yard that might send an errant particle into their detector. But they're ultimately limited by the thickness of the shield you need to get rid of the backgrounds. So if you want to move up and to the right here, okay, you need to make this shield thinner. But at some point, you're not screening out your muons and other standard model backgrounds anymore, and they're gonna hit your detector. And so getting up into the middle here is actually kind of hard, and we really want to do that. How do you do that? The way you do that is actually to measure the decay length, to see where this A prime came from downstream of the target. All right, so how does one do that? So I want to measure how far this A prime travels before it decays to an E plus E minus pair. And if you've seen a few talks by accelerator-based particle physicists, you'd probably say, oh, that sounds pretty familiar. It's a lot like the process of tagging heavy flavor jets, for example, at the LHC, where you're looking for heavy quarks that travel some distance from where they were produced in a primary vertex. And that's a great example, because the way you do it is exactly in the same way. One difference, though, here we need a rejection of things coming from the target of sort of 1 million to 10 million. Here you're just sort of looking to enhance and suppress the background from the primary vertex by a factor of 10 to 1,000. So it's the same game, but it's a little bit different terrain. So again, familiar context for this. What kind of detector do I typically need to do this? Here's CMS at the LHC, which I picked for a particular reason. Don't be offended, Atlas people. So I've got a silicon tracker that I use to measure the trajectories of these to see where the particles came from. An electromagnetic calorimeter to verify that what I see is, for example, an electron and not a hadron that would go right through that. And then I need a magnetic field to curve my tracks that I can measure the momentum in the silicon tracker. Well, okay, that's great, but I don't care about hadrons and I don't care about muon. I'm just interested in the electrons. So basically what I need is just this right here. And that basically is what the heavy photon search experiment is that we built and are operating at JLab. It is essentially a small slice of CMS tracking and calorimetry. So the silicon vertex tracker is built inside of a dipole magnet. So you can see the size of this thing, 1 meter, it's big. It's not quite tabletop, but it's not a huge experiment. And that measures the trajectories of the electrons to reconstruct the mass, the vertex position. And then downstream, we have this lead tungstate calorimeter that identifies E plus E minus pairs with precision timing to reject single electron backgrounds. What do I mean by that? Okay, so you realize most of my electrons just multiple scatter in the target. They spray crap everywhere. So most of my occupancy, most of my physics that's going through here are just a constant stream of single electrons. And I'm not interested in those, and I don't want the hits from those. So if I have a device that can see, that if I have a beam that's basically continuous, okay, not big pulses of electrons, and a device that has very precise timing, I can see when I get both an electron and positron, and I can tag that time and only read out the hits corresponding to that time and screen away all of that out of time single electron background. Okay, so that's basically how this thing works. Here's the SVT, the target just upstream of the silicon, A prime travels a little ways, decays, and the ecal. Now, again, one problem is the graded beam, the scattered beam, has to go right through the middle of this detector. So it needs to be split in top and bottom halves. So that's the way it's built. So this is what the silicon looks like, laid out on a granite table. The ecal also split between top and bottom. Where you see a hint here, so there's a vacuum chamber. We have to transport the beam all the way through the apparatus in vacuum. So this thing has to be built in beam vacuum because if there's gas there, that's an extended target. Okay? And so I'll make standard model backgrounds off of that extended target that look like my signal. So I have to operate in beam vacuum, and I have to have, to get this forward acceptance I need for the physics, I need to have the silicon very close to the beam. And by very close, I mean there's a 1 millimeter gap between these two planes of silicon through which that scattered beam has to pass. It's this sliver of light here. Okay, so this is a small experiment, you know, kind of a few $1 million, but this is not by any means an easy thing to do. Here's a picture of what it looks like from the outside, where we also have to have this, this motion system that opens and closes the tracker, because you can't establish beam through this tiny sliver. You have to open up the device. For people who know the LHC experiments a little bit, this is kind of like a cheap Velo at LHCb, okay? Fine, so HPS operates again at this JLab CBAF. That means the C is for continuous, and that's a definite clue. It's not really continuous. It has a 499 megahertz repetition rate, so bunches every 2 nanoseconds with a very low charge per bunch, again, so I can tag these E plus E minus pairs with the calorimeter and reject these out-of-time single electron events. I need a very small and stable beam spot to keep that, you know, to keep from blowing up the silicon, which you can do, we've found. And you really need to be able to tune the beam energy because that determines the mass range for the search, right? The opening angles that you get in your detector. So we operate between 1.1 and 6.6 GeV, where the detector is part of this 3-magnet chicane in an alcove right in front of the dump. It is not at all a glamorous place to work, I can tell you. Okay, so we had 2 engineering runs, a few days each, right after installing the detector in 2015 at lower energies, 1.1 and 2.3 GeV. This was during the period of commissioning for an upgrade to the CBAF to 12 GeV. So we were lucky to get a little bit of time to shake down the apparatus in the experiment. We did get enough data to develop the analyses and produce our first results. So here you see the z-vertex position as a function of the invariant mass, where this is where you are sensitive to A primes, and you can see there are just a few background events at lower mass. And from that, you can derive limits in this epsilon squared mass plane. With this little bit of data, we're about 8 times the expected rate for this minimal A prime model. There are other models where we have sensitivity already, but we're not there yet with the minimal A prime model. We did identify some key improvements that can make the experiment more powerful. We did those improvements and upgraded the detector and operated to collect our first physics data in 2019 and 2021 at higher energies. where that data is now needs to be really combined to do analysis and get our first physics results. So we're still working on that, but when we have all of our data, this is the kind of sensitivity that we expect to have. All right, so another sip of water time before I completely shift gears. So I've talked enough, I think, about the visible searches. Now let's talk about the case where we're searching for the dark matter itself. So in this case, typically we want a parameter space that's a little bit more natural for talking about searching for dark matter. And so I don't want to just spring that on you. I want to explain it to you. So if I write down this annihilation cross-section, I can pull out this dimensionless parameter, is interaction strength, that controls the cross-section, okay? And if I plot that parameter y as a function of the mass of the dark matter, you can see why I would be able to draw directly on this plot what these relic targets are exactly, where this value in the parameter space would correspond to producing all the dark matter that we see of this type. Again, you know, you're strongly disfavored down below this because you would overproduce dark matter unless you want to play some games, which I'm sure the theorists can do if they want to. Above it is all well motivated because, again, this could be a component of the dark matter. Now, the gray area at the top here are the current constraints from accelerator experiments. And you realize, you know, we measure, again, you know, or constrain mass of the mediator in epsilon. We need to convert it into this parameter space. And so the way that's usually done is by choosing some values near the fundamental limits of alpha dark and this mass ratio that are conservative in stating the sensitivity of the experiment. So they in some way minimize what we say the sensitivity is. There are choices of these parameters you could make where this would all already be ruled out. Okay? There are also choices that you could fine tune. You know, if mass of the A prime is 2 mass of the dark matter, then you have a resonance and actually have much less reach. Okay? But this is sort of the typical choice that's made. But you have to be careful. Sometimes you see other choices made and you need to read the plot. Okay, so that's the parameter space that we're working in. And so how do we actually, you know, do these experiments where you realize we only have 2 or 3 orders of magnitude to cover to basically rule out all of the types of dark matter that are basically allowed in this mass range? So there are really 2 options. So the first one is basically just like the option I already showed you. E137 results are on these plots too. So a beam dump experiment where you bring an energetic and powerful beam in, you produce lots of dark matter that again is forward and boosted, very energetic. It goes through some shield and hits a detector downstream where it rescatters. And that's a cool idea. You're basically making a dark matter beam, diffuse dark matter beam, but a dark matter beam nonetheless. The problem is that you pay this small coupling price both to produce the dark matter and to rescatter it. And so the number of events you're going to see of signal is proportional to epsilon to the 4th, which is a very small number. And so what you find is that you begin to get interesting sensitivity for something like, you know, 10 to the 22nd particles on target, 1,000 coulombs. It's a lot of charge. The alternative is, instead of demanding that you see something in a downstream detector, demand that you don't see anything there. So that's essentially the idea behind a missing momentum experiment. You measure each electron individually as it comes in. It's at the beam energy. It loses most of its energy in radiating off the dark matter. I measure it coming out at low energy. And from that, and then I have a very sensitive and hermetic detector in which I see nothing. So there, my number of single event scales is epsilon squared, and I begin to get interesting sensitivity for something like 10 to the 12 particles on target, which sounds a lot more manageable, albeit not easy, because it's a very different kind of experiment. And I'll explain that. So to put this in context, an example of a beam dump experiment, there are many of them proposed for next generation. You can see here's our friend E137 again, using both electron and proton beams, and they have pretty similar reach. So an example that I'll show you is this BDX, or beam dump experiment at JLab, where we look for production of dark matter in a high-powered beam dump. This is the Hall A beam dump. And rescattering in this cesium iodide calorimeter that's downstream. The key background, again, are cosmics, and in this case, also neutrinos, because you produce a lot of neutrinos here, and actually this kind of picture is going to look familiar because it looks a lot like a short baseline neutrino experiment. And yes, in fact, Miniboon is run in a mode where they've done exactly this kind of search, and that's also one of the lines that is in here. So, these searches are ultimately limited by the available beam currents and energies, but also by irreducible neutrino backgrounds, which aren't really very well known, even in the case of BDX. And so they state, what their sensitivity is for 3, 10, 20 events, assuming that there could be some background. So, if you want to get 2 more orders of magnitude, 3 more orders of magnitude here, you need 4 to 6 more orders of magnitude of charge on target. We don't have any context for how to do that. Sort of a dream idea, if you had, this fabulous International Linear Collider and you put, experiments behind both dumps, this is kind of what you would get to. So that's sort of what we would think of as the ultimate beam dump experiment to search for dark matter, at least in the current time. Okay, so that looks hard. What does the option look like? So how does a missing momentum search work? So the question is, what do I see? And what I see is this energetic electron coming in and this very low energy electron coming out. So if I put in, 4 GeV electron, that's not good. Oh. Okay. Opportunity for another sip. So if I put in a 4 GeV electron, pretty much independent of mediator mass, these are different mediator masses, again, it loses most of its energy. And that's important because if I'm going to do this search with some very large number of electrons, 10 to the 12th or some really big number, there is energy resolution is a thing. So I can't perfectly measure this energy or this energy. So I need to require that a lot of energy is lost to make this work. And I can and still keep most of my signal. I can require that 70% of the energy is lost. So that's what I'll do. And then the other observable is that this electron comes out at a wide angle. So it comes out with a large momentum transverse to the incoming beam direction, where the background just sees multiple scattering in the target, basically. And here, the spectrum of transverse momentum actually depends on mediator mass pretty strongly. And that becomes interesting and important. But we're not going to cut on that. We're going to keep that in our back pocket, okay, and try to do the experiment without using that. Where the really important thing is what we don't see, that's the hard part. We don't see anything else for the signal. Okay, so here's our detector concept. My signal, my outgoing energy is much less than my incoming energy. I've got a tracker that measures it coming in, a target, another one that measures it going out. I use a high field here to measure my high momentum and a low field here to measure my low momentum really well. And that's great. What's my background? So my background is basically, again, regular Baryshnick. And I can hear some people thinking, well, it's a photon. It's going to be measured great in your calorimeter. And that's true, most of the time. I'll see the outgoing energy in the calorimeter. It'll be the same as the incoming energy. But most of the time, ain't going to cut it here. And that's because lots of things can happen to that photon. So at some low rate, I can have muon conversions, or I can have photonuclear reactions that produce hadrons. Now, those will, leave some minimum ionizing track or deposition in my calorimeter, and maybe that's well separated from my outgoing electron. So maybe that'll be okay, but it doesn't have to be. Maybe it won't be well separated, and maybe I'll confuse that as being part of this shower. So okay, I'll probably need something else back here that's behind where any electromagnetic shower would be exhausted. So I need a hadronic calorimeter or something that detects muons, for example. So that'll work. I shouldn't see anything back here for my signal. But there are worse things than that. So you can have photonuclear reactions where you produce at some low rate. You get down to 10 to the minus 10, 10 to the minus 12, a bunch of neutrons or just a couple of really hard neutrons. And neutrons are hard to detect, and things can come out at weird angles. So I'm going to need a bigger boat. I need a bigger calorimeter, and I need better coverage for that hadronic calorimeter. And that's basically the story of how you design this detector, where the important thing is to note that there aren't any impossible backgrounds that involve neutrinos until you get to something like 10 to the 18th electrons. So, real possibility. And that's basically what motivates the design for the light dark matter experiment, or LDMX. So it's an electron missing momentum experiment that's designed for up to 10 to the 16th electrons. So electron comes in, I've got a tagging tracker inside dipole magnet, recoil tracker behind it with a target in between, electromagnetic calorimeter, and a hadronic calorimeter around the sides and in the back. About the size of, say, a delivery van. All right, so 10 to the 16th electrons doesn't sound like a lot, but if you need them one at a time, it's a lot. 10 to the 16th electrons is an electron every 2 nanoseconds per year. So I need a high repetition rate beam. And in this case, the plan is to actually use the LCLS2 drive beam at SLAC. So the LCLS2 drive beam that is used for photon science at SLAC accelerates bunches at 186 megahertz. Photon science kicks out the bunches that they want into undulator lines to produce their X-ray pulses for the photon science program. And all the rest of this poor, unloved beam goes to the dump. So what we can do is fill the rest of the buckets with the beam that we want, put another kicker in the dump line, and kick this beam out into an existing user facility in End Station A. And so that project to do that is called the Sector 30 transfer line. And the facility in End Station A, or the whole thing rather, is really called LINAC End Station A, or LISA. And then in a few years, LCLS2 will upgrade to HEV. And that actually makes our experiment easier, as I'll explain. S30XL is currently under construction alongside LCLS2. It's basically complete. And LISA will deliver beam to End Station A later this year. So there's beam for us. Okay, so what does the detector look like? And having seen HPS, a lot of this is going to look familiar to you. So the tracking is based on what we've done for HPS, where here it doesn't even really break a sweat. There's very little occupancy in the tracker. It's an easy job. So we need a magnet. There are lots of these old dipoles, just like the same model that was used for HPS laying around. We'll refurbish an existing dipole and reuse HPS designs for the detector modules and the readout. So here you see in the tagging tracker, in the full field of the magnet, a long, narrow tagging tracker, the target, and then this wider recoil tracker in the fringe field to get our low momentum recoiling electrons with a large transverse momentum kick. The electromagnetic calorimeter is based on a technology that's been developed for the high granularity calorimeter upgrade for CMS, for the phase 2 upgrade of CMS. So this is silicon pads. So this is a silicon sensor behind this PCB with readout chips. Silicon pad readout with tungsten absorber in between. And what's really beautiful about this device is its imaging capability. So you can see here, a muon, a minimum ionizing particle, an electron shower looking different from a hadronic shower. And that allows us to distinguish already in the eCal quite a bit of the time when there's something there other than just that recoil electron that's overlapping it. And so, by using some even very primitive machine learning techniques like a simple boosted decision tree on very simple features of these showers, you can already eliminate a lot of our backgrounds. And then finally, the hadronic calorimeter will be based on the mu-TE cosmic ray veto, split into two pieces as you see here, made with the same kind of scintillator that's fabricated at Fermilab in the scintillator extruder facility with iron absorber. And this device has very low threshold for detecting things like neutrons, where you can see here the design for the mu-TE cosmic ray veto and the equivalent design for LDMAX is basically the same hardware in a slightly different configuration. So reusing these existing technologies really means that LDMAX is actually quite inexpensive and basically shovel ready. You can build this from a technical perspective anytime. All right, so what does the sensitivity look like? So if you run with 4 GeV beam for a year, you get about 4 10 to the 14th electrons. So we've tended to call that phase 1. And we've done a full study of the analysis using full simulation that was published in 2020, where you see the two big vetoes are this eCal BDT and basically the energy, the largest energy deposition in a single cell in the hadronic calorimeter. So you can see the BDT discriminator value here and the maximum photoelectrons in HCal module here. The signal's way up in this double inset in this tiny red box, where most of the background is very, very far away. But there are about 10 events still in this signal box, where those all, you can see clear MIP tracks in the eCal. So there's a MIP tracking algorithm in the eCal that picks those out. So at least at this level on simulation, we expect we can have a zero background experiment. Now, anybody that works with simulation will tell you, well, I don't trust that, and we don't trust it either. GeanT4 is good for sort of large-scale things, but these really rare photonuclear processes and electronuclear processes, it doesn't do particularly well at, and that was something we learned early on. We did a lot of comparison with data from the nuclear physics community and a lot of tuning and digging around inside GeanT4, finding weird things that it did wrong. And if I had time, no, I don't have time. We are also, and so we made a lot of corrections to GeanT4, which have been folded in to the code base, and we're using other simulation tools, some of which were actually designed to simulate these processes, some of which are export-controlled code to really benchmark this and understand. And we're still in the process of doing that. Now, our transverse momentum can still always be used to eliminate any remaining backgrounds. And I didn't actually show you the sensitivity, but this is what it looks like for 4 times 10 to the 14th. And if you have some background events, this is for half an event, this is for 10 plus or minus 5, it really only hurts you at low mass. Your high mass mediators have such large transverse momentum that it doesn't affect your reach much up there. But the most exciting thing is actually that this transverse momentum can also allow you to reconstruct the mediator mass. Basically, I can fit to these distributions. And from that, I can actually estimate what the mass of the mediator was. So basically, I'm measuring this electron that essentially touched the dark matter. And so by measuring the kinematics of that interaction, I'm learning something about the dark matter. Well, this is really only the first of the possibilities. And I mentioned this earlier, but, oh, sorry. And no, I did show that already. The most difficult backgrounds are really strongly suppressed with 8 GeV beam. Why? Because there's more energy there. You're less likely to miss it. And some of our worst backgrounds are things that actually an interaction occurs in the eCal and something comes backwards out of the detector. And with more boost, that just really doesn't happen. Okay. So we have studied sensitivity at 8 GeV with full luminosity. And it looks like this. There's a paper coming. It's not complete yet. That's why I'm not showing you results. Where we've also realized that there's some additional sensitivity because you can have a hard BREM that then photoproduces neutral mesons that decay. And by looking for neutral meson decay, you're actually also looking for dark matter in this higher mass range. Okay. And then to give you an idea, I've talked a lot about, dark photons in particular. There are many different mediators. They all have different thermal targets. LDMX, has very similar sensitivity coupling-wise. What changes mostly are what the thermal targets are. In many cases, they're ruled out already. But LDMX has really broad sensitivity that's independent of what mediator you choose. There are a lot of other examples. I'm not going to go through them. They're in backup. And also, being essentially an active beam dump, it has sensitivity to these visible signatures as well. And there's a paper here if you want to read more about these. And then zooming out even, and I meant to mention, what's a background for us are electron-nucleon interactions. But those are actually really important to understand for the DUNE neutrino program. They are a proxy for neutrino-nucleon interactions, where very little is known about those interactions in this regime of Q squared and energy transfer. And simulation code that's needed to interpret DUNE results is all over the map here. And basically, LDMX has a program of electron-nucleon cross-section measurements that can improve that situation. All right, and then pulling back further, I've focused on just a few experiments, and in particular HPS and LDMX. But there are many, many different small experiments in this area, both in the US. So these are plots from the SNOMAS R6 paper, but also in Europe with a whole different set of approaches for how to get at this physics with accelerators. All right, and so that brings me to my summary. So particle-like dark matter with thermal origins is absolutely a leading candidate for the identity of dark matter. Searches aimed at WIMPs are being complemented by searches over a broader range of particle masses. Small accelerator-based searches complement direct detection with broad sensitivity to sub-GeV dark matter and dark sector particles, where early searches like HPS are beginning to deliver results, and the next generation, like LDMX, are getting ready to launch. That's it.
Thanks so much, Ken. So, are there any questions? Yes, sir.
Sorry. Sorry, I didn't hear. When you ask that question, it sounds reasonable, but I know it's not possible, and I can't off the top of my head. I haven't thought about it. Let's talk. I think it doesn't work, but I can't off the top of my head tell you why.
Any other questions?
What's the timeline for LDMX?
It's a great question. We're not sure. It basically depends on, when we get a green light. So right now, LDMX is funded as a dark matter new initiative. And so that's basically a portfolio of development and R&D projects. Some of them, only need development and engineering. Some of them need R&D. Where the DOE intends to select from that group projects to build. So we are late in the stage, late in that DM&I process where we're actually preparing our design report and doing engineering design to prepare for a review to approve the project, but we don't know exactly when that will happen yet. In principle, we hope to start next year, but yeah, it's not clear. I'm reading tea leaves. It takes about 3 years to build the experiment, put it on the floor, and get ready to commission it with Beam. So that's the timeline, and then you need a few years of data. I mean, so I guess I'm not sure I'm ready to calculate off the top of my head the mass density of dark matter in that volume, but I suspect it's not terrifically large. But of course, you have to remember, you're embedded in a sea of dark matter in all directions, pulling on you in all directions. So it's a little bit like asking how much gravity you would feel if you were sitting near the center of the Earth.
Okay, hey, I think we're at the end. So if you have any more questions,